Hello everyone, my name is Jishen. I recently graduated from the University of California, San Diego, where I had the privilege of being advised by Professor Zhao. Unfortunately, I wasn't able to attend in person today due to a conflicting schedule with my commencement ceremony. I would have greatly appreciated the opportunity to present this work in person. Today, I'm excited to share our research on compiler-assisted crash consistency for persistent memory. This work tackles one of the most enduring challenges in the field of persistent memory, ensuring reliable crash consistency. Storage technology has been developed from block-based storage devices into byte-addressable storage devices such as PMEM, memory-semantic SSDs, and CXL SSDs. The key differences lies in the update granularity. Traditional block-based devices must overwrite the fixed-size block, resulting in easier atomic updates through additional layer of indirections. With the memory semantic as access to non-volatile storage, we need a more lightweight way of reliably persisting data. To be specific, PMEM is a byte-addressable storage that combines the benefit of DRAM and SSDs, showing near DRAM performance with non-volatility. However, PMEM introduces additional challenge to the software stack, imposing additional overhead for crash consistency or writing additional recovery code. To elaborate on the crash consistency, we present a simple example where CPU is writing a sentence "I love research." While writing it, let's assume that a crash occurred. So in the non-volatile storage, only "I love Risia" were persisted. Upon a reboot, CPU may be loading an incomplete sentence such as "I love Ri," "I love Ris," "I love Risa," and so on. This is regarded as crash inconsistency. To enforce crash consistency, various techniques has been developed, including the write-ahead logging. In write-ahead logging, the CPU would first log the sentence that it will be writing. I'm writing "I love research," for example. Only when the logging is complete and persisted, the CPU would proceed with writing "I love research" in place. This process incurs high performance overhead because it not only writes the redundant information, but also the logging and in-place update has causal relationship, which means the logging must be complete before the in-place update happens. In addition to performance overhead, writing recovery code burdens the programmer. Assuming that the write-ahead logging is deployed, programmer must check whether the log has been persisted atomically, and for each case, determine how to recover the data into a consistent state. We refer recovery code to a set of logic that converts a possibly inconsistent data into a consistent state. In the recovery logic, it determines whether the log is intact. Based on the decision, it may revert to the latest consistent state as in on the logging, or reapply the committed transaction as in redo logging. After running the recovery program, the data is guaranteed to be in a consistent state. Guaranteeing the correctness of the recovery code imposes nonlinear burden to the programmer because they must ensure that both the main logic and its paired recovery code are correct. Following is the simplified logic for programming procedures. Traditionally, the programmer would check for bugs in the code and debug them until there are no more bugs, but PMEM introduces several additional steps. Unlike traditional programming procedures, PMEM introduces nonlinear complications. To highlight some of the additional processes, programmers must additionally check for PMEM bugs, which depends on both the main logic and the recovery code. If a bug has been found, the programmer must iterate through debugging the main logic and updating and debugging the recovery code accordingly. These additional processes are resulting to open problem and cumbersome and error-prone processes. For example, various works for PMEM bug detection has been proposed, but later works identified additional classes of PMEM bugs. Instead of dealing with the open problem and the cumbersome and error-prone process, we propose to automatically generate the recovery from the main logic of the program. With this approach, the PMEM programming does not incur quadratic complication. There are several solutions that may indirectly mitigate the PMEM programming complications, including the Intel's PMDK library, custom PMEM data structure, and some prior compiler-based solutions. Each prior solution has shortcomings, including the limited programming model supported for prior recovery via resumption works such as Clobber-NVM. Our proposal builds upon the recovery via resumption paradigm, where the recovery is defined as running the partially executed code to its completion. For example, given the previous example of the processing writing I love research to the storage, let's assume a crash occurred in the middle. After the reboot, the process would resume execution from the partially executed process and run to the completion. This results in a consistent data state on the storage. For a correct recovery via resumption, the key technical challenge is tracking the program state. These states should provide correct and sufficient information to answer the following questions: where to resume and from which program state to resume from. For these technical challenges, we claim that statically and systematically automated persistence is possible, or SSAPP for short. At a high level, we are proposing recovery via resumption with locality-aware approximate logging. As discussed, we are logging the code execution progress and state. We are approximating the program execution state by eliminating the strict ordering between the logging and the main logic. In our paper, we proved that even without this strict ordering between the logging and main logic, our approach can correctly recover to completion. Another factor that enables huge performance gain is SSAPP's logging storage management. SSAPP shows high cache locality because it statically analyzes the input program and pre-allocates memory for the logging part. This results in many cache hits and thus high performance. The key enabler is RISE, failure reentrant and idempotent section. This is a sequence of instruction without any control flow divergence within the region. For those who are familiar with LLVM, this is a basic block with the following properties. Reentrancy is when a partially executed program state can be reused to re-execute from the beginning without any side effects. Similarly, idempotency is when re-executing the same region multiple times does not incur any side effects. Here is an example of non-RISE code. In C programming language, it is I++ with some additional code that follows it. I++ can be decomposed into 3 instructions in LVM-IR: loading the value, adding 1 to the value, and storing it back to the variable I. This is an example of non-reentrant and non-idempotent code because if I++ has been successfully executed, then re-executing the code from the beginning would result in side effect or incrementing the value twice. Instead, SSAPP would automatically convert it into 2 rises, namely rise n and rise n plus 1. The 2 rises are executed back-to-back with unconditional branch, retaining to the original execution logic. Because each rise is read-only or write-only, there is no side effect of re-executing it multiple times or re-executing it from the beginning using partially executed memory state. Therefore, each rise is reentrant and idempotent. To track the program execution status, we deploy the proposed techniques: load to persist, torn bit for store atomicity, and crash build. These techniques collectively create a systemic way to track the execution status of memory operations within each rise. For example, if all of the memory operations within a rise has the same torn bit, then the rise has been executed atomically and should not be re-executed during the recovery. At a high level, SSAPP involves three steps. First is analyzing the input program and converting it into sequence of rises. In the leftmost diagram under label before, we show the control flow of the input program. Each node is a basic block where some nodes happen to be read-write and write-write. For those that are not write, SSAPP converts them into a back-to-back nodes where each node is a write. After the conversion, the second step is applying the lightweight program state tracking process for each write. The details of each techniques is in the paper. At this point, we have the main logic program with compiler-inserted logging techniques for crash consistency. In the last step, the SSAPP further converts the main logic of the program that prepends the resumable write computation logic. The logic takes in the memory state and runs through the algorithm and branches into one of the rises. To clarify what SSAPP does, it takes a volatile program in LVM-IR as input. It outputs two executables, the crash-consistent main logic of the program and the recovery program with a new entry point that first computes the resumption location. The conversion goes through the three systematic processes. First, SSAPP preprocesses the input program so it becomes piecewise write by inserting unconditional branches. After inserting approximate logging to track the program execution progress, the main logic is now crash consistent. By further inserting the program resumption logic, the SSAPP auto-generates the recovery program. For empirical evaluation of crash consistency, we developed an emulated crash framework. Given the crash-consistent program, we further modify it to have a conditional branch that may jump to the process termination instructions. The modified framework would load the environment variable of the target write ID. When the target write ID has been executed, the conditional branch would skip over the remaining execution and exit the program. This effectively emulates a sudden crash, leaving a partially executed memory state. Then we run the auto-generated recovery code to recover the consistent memory state. For the litmus programs that we tested, including the I++, our recovery code successfully recovered the consistent state from all possible partially executed state. With these techniques, SSAPP improves the throughput by 1.8x compared to the prior state-of-the-art Clobber-NVM under EADR. Unlike the Clobber-NVM, which cannot support the lock-free data structure, SSAPP shows on-par performance with Mirror, a human-optimized lock-free data structure for PMEM. For TATP, SSAPP performed 7.5x higher performance than Clobber-NVM. This is because TATP transactions have smaller number of load instructions. This results in smaller number of total rises and thus smaller total overhead, reaching the near theorem performance. We further evaluated the scalability of SSAPP. SSAPP showed 1.4x higher throughput than Clobber-NVM when varying the number of threads. For lock-free data structures, SSAPP showed comparable scalability to Mirror with a slightly slower performance for list data structure. To conclude, we propose SSAPP, which automatically generates crash recovery for PMEM through compiler-inserted persistence that improves performance and supports wider programming models. Thank you, and I'm open to questions.
Let's just do a quick audio check to see if we have our speaker there. Yeah. Are you online? Can you hear us?
Yeah, I can hear you.
Terrific. Okay. I'm Steve Blackman. I'm the session chair. Now I'll just ask if we have any questions.
Hi, Eres Petrang from the Technion. There was a work by Guy Blalock and Naama Ben David and others in SPA about forming this repeatable code that you can redo when you fail, and splitting the program to several of those. Are you aware of this? Or maybe I can send it to you offline.
That'd be really helpful. Thank you.
And there was also a work in P-pop where they had a bit in each word saying if it was, or a related bit in each word saying if it was already persisted or not, which also seems related, right? And I don't
Uh,
know.
so the bits here is not about whether it has been persisted or not. It's like sort of versioning of each cache line. So it's for every one of the cache lines that access or access within those basic blocks are identical, then it's regarded as the atomic execution of that code region. So it doesn't necessarily mean that it has been persisted or not.
Right, right. Okay, I will send you these two papers and you'll see if it's connected.
Right. Thank you.
Okay, thank you.
Ah, thank you for the great talk. And I wonder, do you know the research named Memento that presented in PLDI 2023 maybe? It also solves same problem and it uses not compiler but persistent cas instead. And if you know it, and I wonder why there is no comparison with that framework. Thanks.
Could you repeat the name of it?
Memento.
Oh, um, yeah. So this work was mostly work before 2023. So from for comparison onward from 2023, I admit that it's a bit lacking, and thank you for mentioning that out.
Okay. Do we have any further questions in the room? All right. If not, let's thank the speaker for a great talk.